Great. So welcome everyone. This is the last 1W-MINDS seminar of the semester. Today we have Selin Aviyente from Michigan State University, and she's going to talk about multiview graph learning.
Okay, thank you. So good afternoon or good evening. So today I'm going to talk about the problem of graph learning from multiple data sets. So first I'm going to give a brief introduction to graph-based data science, because in a lot of modern data science applications, the data has a graphical structure, and how do you learn from this type of data? After that, I'm going to talk about the problem of learning the topology of the underlying graph from the observed data. And this problem has been extensively addressed with the assumption that the data is homogeneous and has a single graphical structure that describes it. So we're going to, in this talk about two problems that are extensions of this. The first problem will be multi-view graph learning, where I'm assuming that you have data observed from multiple closely related graphs, and how can we learn the graphical structure jointly across these multiple data sets, while learning also a consensus graphical structure. In the second part of the talk, I'll extend this problem, where we assume that the observed signals are heterogeneous or mixed, and where we want to learn both the cluster information and the graphical structure for each of the clusters. Finally, I'll give some conclusions and suggest some directions for future work. So modern data analysis involves large sets of structured data, and this structure is usually encoded in the form of graphs. So this is an example of what we call a graph signal, where you have signal values that are defined on the nodes of a weighted and undirected graph. And the signal values on the nodes carry information of interest. So this could be a social network, where the graph may encode the relationships between the different people in the network. And the signal values would be the attributes, like the personal interest of each one of these nodes. And these values, the graph signals, are related to the topology of the graph where they're supported. And graph signal processing actually leverages this relational structure to make inferences. So it doesn't only use the signal values like in traditional signal processing, but it also uses this additional structural information to learn from this data. So some examples of graph signals. So I'll start with this example on the right, where the graph is a proximity network between different locations in the United States. So the nodes in this graph are different locations, different cities, and the edges are their physical connections between these cities. And the node values, or the actual graph signal, is the temperature recorded in each one of these cities, which is encoded by this color map. So what you observe here is that cities that are close to each other have similar signal values, whereas cities that are farther from each other have different values in terms of the graph signal. On the left, we have an example from neuroscience, where you're recording from the brain, neurophysiological recordings from different locations in the brain. And the graphical structure may be the structural network, which may be inferred using magnetic resonance imaging. So you can either look at this signal as a multivariate time series, where you have the signals varying across time at the different locations. But if you look at it as a traditional multivariate signal processing framework, you would be really not considering the relationships between these different signals, or the proximity of the locations from which these signals are recorded from. The other view is the graph signal processing view, where you have the graphical structure shown here, and you can take a snapshot of this graph signal at a particular time point T1, where it will show you the amplitudes of the signals at these different locations at that particular time point. And on the right, you see the same, the graph signal at a different time point. So this would be an example of a time varying graph signal. In both of these examples, we saw that you really need to have the graph topology in addition to the signal values. However, in many applications, graph topology may not be known or cannot be directly observed. So for example, in the case of the temperature data, if the graph is the physical network, you would be able to actually observe it or record it. However, in the case of the brain network, the graph topology has to be inferred from some other recording, such as an MRI recording. So examples where graph topology is not readily known include functional brain connectivity, regulation among genes, where you observe the expression of the gene expression profiles, but you don't actually observe the regulatory network underlying the observed gene expression values. So in this case, the goal is to infer the graph topology that captures the underlying relationship between the observed graph signals. So given the graph signals, what is the underlying topology that makes the most sense and learning a graph? And this problem has been addressed in various literatures. The most classical approach has been statistical models using methods like correlation networks. So you could use things like Pearson correlation measure to construct or infer a graph, or Gaussian graphical models or graphical lasso. In these methods, most of the time, there's an assumption that the data is Gaussian distributed. Then there's the second class of models, which are physically motivated models, where it's assumed that the observed graph signal is a diffusion process on the network. And using concepts of graph stationarity, you can model the graph signals as filtered versions of stationary white noise on the graph. And the last class of methods are based on the smoothness assumption, where you learn a graph over which the data has some sort of regularity. So in this talk, all the methods that I present will belong to this last class, the graph signal smoothness-based models. So in order to formulate our approach, first I'll introduce the concept of what is smoothness of a signal on a graph. So simply stated, smoothness says that vertices that are highly connected with each other should have similar values. So if two nodes I and j are connected by a large edge weight, then the values of xi and xj should be similar to each other. Why does this make sense, or how is this relevant in actual applications? So you can think of a geographical network like the temperature data I presented, where the nodes represent locations, edges are their physical proximities, and signal values are temperatures. So in this case, locations that are highly correlated with each other, that are close to each other in terms of physical proximity, will have temperature values that are similar to each other as well. Or in social networks where nodes may represent people and edges their friendship relationship, and the signals are the personal interest, then you would expect that people who are close friends should have similar personal interests. So that's what we mean by a smooth graph signal. And here is another example of where you're observing the same graph signal. So in all these cases, the graph signal doesn't change, but given a graph signal, you can have different graphical structures, G1, G2, G3. So if we use the assumption that the signal is smooth with respect to the graph, we would choose the topology G1. Why is that? Because you can see that in G1, the connections are always between nodes that have this similar values. So nodes that have red values or positive values have edges between them, and nodes that have blue values or negative values are connected with each other, but you don't have any edges, direct edges between positive and negative valued nodes. Whereas in G2 and G3, you do have nodes that are connected with positive and negative values. So if the goal is to minimize the smoothness or to obtain a smooth graph structure, then in this case, you would choose G1. So mathematically, the way to formulate this is that it's been shown that learning the graph topology is equivalent to learning the graph Laplacian. So given a weighted undirected graph described by the set of nodes, edge set, and the edge weights or the adjacency matrix, the combinatorial graph Laplacian is defined as the difference between the degree matrix and the weighted adjacency matrix. The smoothness of the signal x with respect to this graph is then quantified using the quadratic form of the Laplacian given in this format. So what this says is that if Wij is large, in order to minimize the smoothness, the values of xi and xj should be close to each other. Well, Wij being large implies that nodes I and j are strongly connected, and you would expect those nodes to have similar values. So the goal would be to, when we're learning the Laplacian with the smoothness assumption, the goal will be to minimize this quadratic form. So this problem has been formulated by Dong and has been extended by others. The idea is that given a set of signals, AMP signals, learn a graph such that the signals are smooth with respect to the graph. And this is formulated as an optimization problem where you're minimizing the smoothness across all these observed signals. So that's the graph Laplacian term. And with an additional regularization term that ensures that the learned graph is sparse. With some constraints, ensuring that the learned matrix L is a valid Laplacian, which means that it's symmetric, its diagonal has to be 0, and etc. So all this literature has been focusing on the case where all the data points follow the same relational model described by a single graph. So assuming that the observed signals can be described by a single graph. However, in a lot of real applications, data may be coming from multiple closely related graphs, which we call multi-view graphs. So some examples that I will refer to all throughout the talk. One is single cell RNA sequencing data, where you may be measuring this gene expression profiles from closely related cells. So cells that are from the same tissue, which will have very similar gene regulatory network structure. Or neuroimaging data, where you may have a group of subjects that are doing the same task, so you would expect their connectivity networks to be more or less similar. Or social networks where you have the same group of people interacting and you're looking at their different types of interactions like friendship, collaboration, etc. So the goal in this case will be to jointly learn these multiple related graphs rather than learning each view individually. So we're claiming that learning them jointly will actually improve the performance and accuracy of the learned graphs. There's some prior work or closely related work in this area. The first class of methods were actually not on learning from multiple related graphs, but were on time-varying graphs. So the idea there was to learn time-varying networks, assuming that the variation across 2 consecutive time points is smooth. So our formulation will be similar to this in terms of the smoothness assumption, but in this framework, they only consider 2 graphs at a time. So they're only jointly learning 2 graphs at a time with a smooth variation assumption. The second or more recent work looks at the joint inference of multiple sparse graphs with a graph stationarity assumption. So they do not use the smoothness assumption, but more of a diffusion model. And they use a pairwise similarity to regularize the problem so that the multiple graphs, learned graphs, are similar to each other. So in our approach, in addition to learning the multiple views individually, we also learn a consensus graph. And none of these previous papers really look at that. So I'd like to motivate why we also want to learn a consensus graph. So in the gene regulatory network inference problem, where you have a tissue and you have different cell types from the same tissue. So these cell types are similar to each other and their gene regulatory networks will be similar. In this case, we may be interested in learning the individual or cell type specific networks, as well as a common network that really describes this particular tissue. Or the other example would be in neuroscientific applications, where you have each subject's electrophysiological or neuroimaging recordings, and you may be interested in learning subject-wise or subject-specific networks, as well as a task-dependent network, which summarizes the task-related activities. So these are just some examples where you may be interested in learning the consensus graph in addition to learning the individual graphs. So the framework assumes assuming that you have these observations from the AND views, and learns a graph for each view, assuming that the signals, observed signals, are smooth with respect to this graph. However, instead of learning these graphs individually, we also add an extra constraint that these individual views are similar to this consensus graph. So it has two parts where there is a joint graph learning and there is a regularization through a consensus graph. So this can be formulated as an optimization problem where the first two terms are similar to a single view graph learning, where the first term ensures the smoothness of each view with respect to its own graph. And the second term ensures the sparsity of each view's graph. The third term ensures the consensus between each view and the consensus or the global graph. And the last term is a regularizer on the consensus graph, with subject to the same constraints as before. So there are three cases that we can consider in terms of how to choose these consensus term and the regularization term. In case one, which is the simplest thing that would probably come to everyone's mind, is we minimize the similarity between the L2 norm of the difference between each view's Laplacian and the consensus Laplacian, and use a regularizer that ensures the sparsity of the consensus graph. The second approach would use a L1 norm for the consensus error. In this case, using an L1 norm basically encourages sparse differences. What that means is that it actually leads to local constancy of the adjacency matrices. So the difference between the consensus graph and the individual views only deviate from each other at only a small number of edges. And in that case, the consensus graph automatically becomes sparse, so we don't need this regularization term. And in the final case, this is equivalent to, it's an L2-1 norm. What that does is it encourages sparsity in each group. So edge weights in this case can vary significantly for a few views at a time. So most of the views are consistent with the consensus, but a few views may be different. In this talk, I'm only going to focus on this first case. So in order to formulate this optimization problem, we basically rewrite this trace term and write it as a kernel function. And then we vectorize all the matrices by taking advantage of the symmetry. So the Laplacian matrix is symmetry and XI transpose is a symmetric matrix. So we can just use the upper triangular part of these matrices and vectorize it and write this optimization problem in this way. So this will be solved in two stages. So one is fixing L and solving for LIs, the individual views, and then fixing LIs and solving for L. So in an alternating way, using Prox linear block coordinate descent algorithm. In the solution of Li, we use approximate Prox linear update to encourage faster convergence. And for solving L, we solve it exactly using proximal operator. So the convergence of this is guaranteed based on prior work, since our objective function consists of smooth terms and separable non-smooth terms. And there are a couple of hyperparameters. And the major ones, if I go back, are alpha, which controls alpha, and gamma, which control the density of the learned graphs. So alpha controls the density of the individual views, and gamma controls the density of the consensus graph. So we can choose it to obtain a desired density level if we know a priori what's the density level we desire. And beta controls how similar the different views are. So we can set an average pairwise similarity based on prior knowledge if we know, and we can choose beta based on that. So these parameters are really application dependent. And if there is any prior knowledge from the domain, like in gene regulatory networks, we know the graphs should be sparse, so we can select these parameters accordingly. So first, I'm going to show some results on simulated data. So for simulated data generation, we used random network models. So we use two different random network models. One is Erdos-Renyi network model, and the other is Barabasi-Albert network model. And we generate N views from this random network by perturbing a certain percentage of edges of G. And for each one of these Gs, we generate the graph signals. And the way we generate the graph signals is we first generate normal Gaussian signals, a signal matrix, and then we apply a low-pass filter. The important thing about this low-pass filter is this low-pass filter is a function of the Laplacian of that particular graph. So it uses the eigenvalue distribution of that particular Laplacian in this manner. And it is low-pass filter because it looks at the square root of the pseudo inverse, which means it emphasizes the low frequency or the low eigenvalues. So it's a low-pass filter. So why we do it this way is that in this way, we ensure that the generated signals are smooth with respect to the graph. So it actually adheres to the assumptions we made in our framework. And then we add some additive white Gaussian noise. So in the first case for the Erdos-Renyi model with 50 nodes with a probability of edge at connection point 2, we generated 3 views using 20% perturbation. On the left, what we're showing is, so we quantify the results using average area under the precision versus recall curves. And on the left, we're looking at the accuracy of graph learning by doing single view graph learning. So if I learned each view separately and average the accuracies versus if I learn each view using the proposed multi-view framework. So what we see is that even with decreasing SNR, signal to noise ratio, with multi-view learning framework, there is a significant increase in the accuracy of the learned graphs. So versus learning each individual view separately. On the right, what I'm showing is the performance of the learning the consensus graph. So consensus graph is in this framework, it's not like it may not be the end goal, it's more like a side tool to ensure the similarity of the individual views, but we still look at whether we get a consensus graph that makes sense. So to do that, what we did is we got the data from the single view data and concatenated them and learned, just apply regular single view graph learning and learn a single graph structure from this concatenated data. So that's what the blue bars show. And the orange bars show the graphs learned, the consensus graph learned from multi. So there is not a significant difference. I mean, there's maybe a slight drop in the AUPRC, but it's not really statistically significant. We observed similar results for the other random model, the Barabasi-Albert model. And again, in this case, we see that learning jointly improves the results. And the consensus graph is almost the same, whether you concatenate the data and learn a single graph, or whether you learn the consensus graph through this framework. Next, we looked at real data from single cell gene expression from mouse embryonic stem cells for differentiation. In this case, we had data where each view corresponds to cells from 4 states, so 4 different time points. The first time point is before this leukemia inhibitory factor withdrawal, day 0, and the other 3 time points after. So those are the 4 different days. And what we did is we learned the graphs for the 4 views, and we learned the consensus graph. And after we learned the graphs, we identified hub nodes. So what we are showing here, these are the different genes, and whether they're hub nodes or not are shown by these purple dots for each one of the views and the consensus graph. So one thing that we notice is that if a gene is selected as a hub node, in most cases, there are some exceptions, 1 or 2 exceptions. In most cases, that means that there is at least one view that also identifies this as a hub node. Other things are some biological interpretation. So regulator genes that are known to play an important role in early stages of differentiation, like day 0, which is the first view, they play an important role in differentiation, and we correctly identify them as hub genes in G1. So if we look at this SOX2, it's identified as a hub gene in the first day, and it's also found as a hub gene in the consensus graph. Another example of this is we obtain around here this gene, and it's identified as a hub gene again in first view and in the consensus. So this is some biological interpretation coming from our collaborators. And we also identified some other genes, markers of pluripotency early on as hub genes. So this is just an example of how this framework could be useful in a real biological application. Now I'm going to move on to the second part where we extend this framework further. So in the first problem, we assume that you're given multiple data sets and you learn the graphical structure describing each data set. Now we are given a heterogeneous or a mixed signal model where we don't know the different data sets, so we don't know the different clusters. And we need to learn both the clusters and the graphical structure associated with each cluster. So one example of this could be in the brain, fMRI data, where you're measuring the signal across the whole brain. And the different signals may actually correspond to different brain processes like cognitive control, auditory processes, or vision, etc. And each of these processes can be explained by a different brain network. So within the big functional network, usually people are interested in subnetworks like the visual network or the auditory network or the control network, etc. So it's not clear which network is activated at what time. So you want to separate the signals that correspond to different networks and then learn each network. So that's kind of a motivating example. So the goal is simultaneously cluster the data and learn the representative graphical structure for each cluster. There's been some very recent work in this area. The first one is the graph Laplacian mixture model, where they extend the smooth graph learning framework to jointly model the smooth graph signals and identify clusters through Gaussian mixture model. Of course, this model assumes that the number of clusters is known and that the data is Gaussian and uses an expectation maximization algorithm. The second approach with K-graphs, it extends K-means clustering. So instead of where in K-means clustering, you would assign each signal to a cluster by looking at Euclidean distance. Now they assign signals to clusters based on whether that signal is smooth with respect to that cluster's graphical structure. And it's done in an iterative manner. So both of these methods assign a graph signal to a cluster based on graph smoothness, only the graph smoothness of the signal to the cluster graph, but they do not take the similarity between graph signals into account. However, we all know that the basis of clustering comes from graph similarity. So our goal is to combine smoothness with respect to the cluster graph with the pairwise, with additional information in the form of pairwise similarity between graph signals. So this is an overview of our framework. So let's assume we have x1 to x11. These are graph signals. And each of these graph signals is defined on a graph of 6 nodes. So the graphical structure with 6 nodes. There may be some relationships between these 11 graph signals, which is captured by this graph GC. So what would be the usual way of clustering these graph signals is something like spectral clustering. So you can use spectral clustering and learn the different clusters. So what we're doing is we're not only using spectral clustering, but we also want these signals within a cluster to be smooth with respect to their respective graph structures. So we also learn these graph structures over these 6 nodes, where each cluster is smooth with respect to its own graph. And we use this as a regularization in the spectral clustering. So we are simultaneously doing spectral clustering and learning the individual cluster-specific graph structure. So the problem statement given is that you have P graph signals, and for you have a collection of graphs G1 to GK corresponding to the K clusters you have, and each cluster is represented by GS. And it's important here to note that GS is defined over the same node set V of size N. And in addition, you have some side information in the form of GC, where this is a graph that encodes the similarity between the graph signals. So VC is a graph with P nodes, since you have P graph signals. So the goal is to find the partitioning of the graph signals. So you want to partition these P graph signals into K clusters, where CS is the cluster of graph signals defined over graph GS. Of course, you can learn C by doing spectral clustering on GC. However, this does not use the fact that these are special graph signals and they have some additional structure, so it doesn't take that into account. So in order to address this, we propose a regularized graph cut. So regularized spectral clustering, or first regularized cut. So the first term here is a regularized cut defined over GC. So WIJC is the adjacency of that similarity. And this just counts the number of edges between the different clusters. And we add a regularization term such that each signal is smooth with respect to its own graph or its Laplacian LS. So this is just the graph, this is the quadratic Laplacian term that quantifies this smoothness. And we have an additional delta function, which basically says only consider the signals that have membership to class or cluster S. So it separates the signals into the clusters. So this does, we ensure that the signals are smooth with respect to their cluster graphs. Of course, this is an NP hard problem. So in order to address this, we can relax the problem by first defining Z as a binary cluster membership matrix. Then we relax Z to take on real values, and we can write the regularized cut. So relaxed version of graph cut becomes this trace norm over LC. And the smoothness term, instead of this delta, we have this Z that relaxes this problem. So what this does is it's again counts the number of signals within that particular cluster. So it only looks at the smoothness for each cluster separately. However, in this optimization problem, the goal is to learn Z. However, we are assuming that we know LC and LS, which may not always be the case. So we need to know these two graphs, two Laplacians or sets of Laplacians to be able to find Z. So GZ, the graph similarity matrix or adjacency matrix, can be learned using either graph learning methods, or you can construct it using k-nearest neighbor graphs, classical approaches. However, the graphs in G, so the graphs that represent each partition, must be learned simultaneously with clustering. So we extend the regularized spectral clustering to add on graph learning onto it. So now we're not only learning Z, we're also learning L1 to Lk, these k Laplacians, where this term is the same as before. This is the regularization, but since we're adding the graph learning, we also add this term that ensures the sparsity of each cluster's graph. There is a slight modification here with this term. What this does is this corresponds to the number of signals in that cluster S, because the different clusters may have different number of signals. Since alpha 2 is a constant, so for a given alpha 2, we want to make sure that, I think there's a question.
Yes. Do you see here as learning the graph with the spectral constraints, like constraints on the eigenvectors, so that the spectral clustering of the graph matches the clustering of the signals? Is that a way to interpret what you're doing here?
Right. So the first term is actually spectral clustering of the signals, right? Mm-hmm. That's exactly what it is. The second and third term is, the second term ensures that the signals in a cluster are smooth with respect to their own graph, and that these graphs are sparse. That's what the second and the third term do.
Thank you.
Okay. Right. So this term is basically to balance, to ensure that the sparsity levels of the learned graphs are similar for a given alpha 2, and that it's not affected by the size of the clusters. That's what this term is. So this is a regular, this is our framework. And again, because of the symmetry of these Laplacians, we can reformulate it using vectorization. Again, here we assume LC is known. And it's again a non-convex optimization where we use block coordinate descent and optimize over each variable while fixing the others. So I'll show first some simulation results and then some result on a real network, but I'll consider two different cases of simulation. And we'll compare our method, which we call GRASCale, to both clustering and graph learning, because our method has two goals. One is to do clustering, and the other is to learn the graphs for each cluster. So in terms of clustering, we compare with spectral clustering, since that's a benchmark. And we also compare with these two recent methods, GLMM and K-graphs, since they also try to do the same thing. And for graph learning, we compare with just regular benchmark graph learning algorithm and GLMM and K-graphs. In our case, we still assume that the number of clusters is known. So this graph in the first setting and the first experiment, the way that these graph signals are generated are exactly the same as before. So I generate a random graph model, and then we perturb them. And then from the perturbed graphs, we generate smooth signals. This is exactly the same as I explained before. So I'm assuming we have three views, and each view is generated by perturbing the random graph model a certain number of times. So here on in the top, what we're showing is the F1 score that quantifies the graph learning performance, and in the bottom, we look at the clustering performance. And the x-axis is the perturbation level. So as we increase the perturbation level, what happens is that the different views become less similar to each other, which is actually good for our framework because it will make it easier to separate those signals. So as you can see, as the perturbation amount increases, the performance of our clustering algorithm gets better, and that's the case for the other two algorithms. But we're still better than the GLMM and K-graphs. Spectral clustering does not do well in this case. The reason is that across the different views, these data are generated independently. So there is no correlation, or there's no like a structure that spectral clustering can use. There's no similarity between the graph signals that is imposed. So spectral clustering does not really do well, whereas our method can actually cluster them. In terms of graph learning, of course, the benchmark graph learning does the best, which we expect, because the GL assumes that the partition is known. So the partition is given to the algorithm and it learns the graphs. So the ground truth is known in terms of the partition, whereas our method and the other two have to simultaneously learn the partition and learn the graph. So we're doing slightly worse, but as the perturbation amount gets increases, our performance gets actually closer to GL. In the second setting, what we do is we try to impose some sort of a similarity between the graph signals. The way we do that is we actually construct GC using a planted partition model, or like a stochastic block model with 3 blocks, equal size clusters with a certain probability of intra-connectivity and intercluster connectivity with a mixing coefficient. So as you increase the mixing, the clusters become more mixed and it will be harder to do spectral clustering or separate the clusters. We again generate X0 as before, but now we apply a low pass filter defined by this graph GC, so that the correlation structure of GC is actually injected so that the signals have that structure as well. And then these X0s are filtered with the low pass filter in the first case, again, to make sure that they're smooth. So this ensures the smoothness, and the first step ensures the similarity between graph signals. So in this case, if we look at it, spectral clustering actually does better. Does better compared to the previous case, but still we actually perform better than spectral clustering, which shows that taking the graph smoothness into account makes a difference. And in both cases, the performance drops as mu increases. In terms of graph learning for both random network models, we're pretty close in terms of graph learning to the benchmark model in both random network models. So then we look at real data. So this is a simple example where we look at mNIST data, where we cluster the data, but we learn a graph for each digit. So we vectorize the 400 images corresponding to digits 0, 1, 2, and 3 to obtain the data matrix where the rows correspond to the different pixels. This shows our clustering performance. So GRASCale, our performance is here, which is higher than regular spectral clustering, and we do better than GLMM and K-graphs. In terms of the graphs that we learned for each cluster, we actually plot them out. So each dot here is like the nodes of a graph, and the edges, we only show the top certain percentage of the edges. So what you see here is that the learned graph structure is actually maps to what we expect to see. So this also provides a way of more interpretable clustering where you can actually visualize the cluster. The only one case is the digit 1, where you have maybe a more of a variation within the cluster. And that's most likely because in mNIST, there's a lot of variation in the way that people write the digit 1. So to summarize, we considered multi-view graph learning in 2 different settings. In the first setting, where we know we're given multiple closely related data sets, we learn the graph for each view individually and learn a consensus graph. In the second case, we have heterogeneous data with unknown cluster information, where we did joint clustering and multi-view graph learning simultaneously. But in both cases, we show that joint graph learning actually has benefits over learning each view individually. And combining these pairwise relationships, in addition to the smoothness, actually provides a new way of doing signal clustering on graphs. And it improves both the clustering performance and the graph learning performance. So I did show some examples, but there are more applications possible. So biological data, as I showed, where you have data from multiple closely related cell types. Brain networks, where you need to learn graphs from multiple subjects or tasks. Or social networks, where you may need to learn multi-layer networks across different social media platforms. So in terms of extensions, so in multi-view graph learning, one thing that we're right now considering is different ways of doing the consensus graph learning by changing the regularization terms, and also looking into regularization using pairwise similarities without the consensus graph. In terms of simultaneous graphs, signal clustering and learning, we can also learn GC instead of constructing GC using KNN or assuming that it's provided to us. We can learn it simultaneously with the others. Another extension would be to learn, consider the case of hidden nodes, where some the signal values may be missing on certain nodes, so missing data cases, or where GC is corrupted. So these types of things can happen in real data, especially in the single cell gene network, where you have a lot of missing data or zero entries. So that would be an application. So finally, I'd like to acknowledge the national support from National Science Foundation and the help of my collaborators. So my student, Abdullah Karaslanlı, actually has done most of this work, and our collaborators in the statistics department at MSU. So thank you, and I'll be happy to answer any questions.
Thank you so much, Selin. Very interesting talk.